Okay, well, thank you very much. Thank you for inviting me. And today I'm going to talk about two projects, both of which I lead. One of them is infrastructure for computer science research, and the other one is really an application that was built on top of that infrastructure. So, in a sense, we're talking about scientific instruments that try to bridge the gap that Dan highlighted in one of his slides, the gap of how many people are working on foundational research, foundational AI research in academia versus industry, right? So we're trying to make it possible for people in academia to work on more foundational research in computer science. So the first system I will talk about is called Chameleon. It's called Chameleon for a good reason, because it's a system that adapts itself to your research needs. Right? So chameleons like to change, and this system you can reconfigure on bare metal level. You of course have root. You can boot from custom kernel. You get access to performance counters, and so on and so forth. Right? And we do that because we support experiments in performance management, in energy efficiency, people who develop new operating systems, and do computer science, work on computer science topics of that kind. We do also support a smaller cloud, a KVM cloud, which is easier for computer science education projects as opposed to research projects. And this also does support some research projects that can be executed on that kind of infrastructure. In terms of hardware, like I'm saying, we're trying to make bare metal access possible to people who otherwise wouldn't be able to afford it. But of course, we don't have access to unlimited scales, so can't compete with industrial scale, but we try to compete on a diverse hardware. So we've got a range of different FPGAs, GPUs, a range of various memory units so that people can benchmark them, try it in one, and move on to various different configurations. And all of that is right now distributed over University of Chicago. Our hardware is in the ALCF machine room at Argonne. So I've got a joint appointment between Argonne and University of Chicago. And the rest of it is currently at TUC. Now, Chameleon was, well, we just got a proposal accepted. So Chameleon was funded for another 4 years of operation last fall. And as part of that Chameleon phase, we've got NCAR joined Chameleon. So we've got 3 operating sites now, 3 of them rather than just 2. And then, but in addition to that, we also have volunteer sites. So people who decided to operate Chameleon on their own without being funded in order to provide resources for computer science. And there are different motivations, a range of motivations for that. Some people are just gathering experience or wanting to demonstrate experience in that kind of operations. Some of them are supporting student competitions or creating multi-purpose, general purpose centers. So there's a range of things that they do. And then lastly, an important thing to know about Chameleon is, as a general philosophy, we're trying to be as mainstream as possible. Right? So rather than build an in-house infrastructure to support this kind of computation, we decided to base it on OpenStack, which many people know as cloud infrastructure, typically used in virtualized configuration. We use it on bare metal. It has a component called Ironic, which allows reconfiguration on bare metal. So we use it largely on bare metal. Again, we have a smaller investment in KVM, also using OpenStack. But in order to adapt OpenStack to our use case, we had to develop some special features. We had to add features to support science, like access via federated login, but we also had to support features like network stitching to support networking experiments. Some of the features we added to OpenStack. So, for example, advanced reservations. So, the ability to reserve resources to be available in advance is something that was contributed to OpenStack back in 2017, largely through the efforts of my team. Right, so it's a range of features, and they all have kind of different fate depending on relevance. So just to give you an idea of scale, at this point, Chameleon is a virtual facility that was in existence almost 10 years. So the project was in existence over 10 years, but we went into production at the end of July 2015. So we've been celebrating our 9th birthday last year. Over that period of time, we had the privilege of serving almost 12,000 users. Just a few users missing. I was checking today, hoping the counter would turn over, but no. So almost 12,000 users working on over 1,200 unique research and education projects, right? We also support emergent applications projects, but it's largely for the purposes of computer science research. And that community collectively produced over 700 papers. So a largish community, very productive. Every month we've got about 600 to 700 unique users logging to Chameleon. So there's quite a bit of busyness in the system. It's a quick map of Chameleon hardware. And as you can see, we've got all sorts of diverse resources at both University of Chicago and at TAC. A few years ago, we developed something called Edge, stands for Chameleon Infrastructure at Edge, that allows you to add edge resources. So single board computers like Raspberry Pis or Nanos into the system and do computation in edge to cloud continuum. And I'll switch to that shortly. As I said earlier, this year, NCAR is also joining Chameleon as a third site. Doesn't have it's been a Chameleon volunteer site. It's got some ARM Thunder nodes on site, but it doesn't have its new hardware yet. And then in addition, we've got volunteer sites, and we collaborate with a range of projects in networking. So when you come to the system, what do you see? How does this work? And the simple answer to that is that it works exactly like a cloud. It's an OpenStack cloud, right? So there's nothing very special there. A few things to call out is we support advanced reservations, right? So unlike commercial systems, we were never trying to create the impression of endless resources. We knew that our resources were going to be always very finite. We don't have the budget for any kind of endlessness in that space. So you can reserve resources. You can reserve resources for a week from now, which is useful for people who want to create demos, have paper deadlines, teach classes, and so forth. We support right now a spectrum of reconfiguration methods. So bare metal is the main one, but we of course do also support KVM and containers on edge resources. We support network switching, orchestration, and so forth. And all of that is available via federated identity access. And so one last thing to know about Chameleon, it's not just a system, it's also a community, a very engaged community of mainly computer science researchers, so people who do very innovative things. So it's a productive community, it's a very happy community, except when a little bit unhappiness sets in because somebody can't run a certain kind of experiment. And several years ago, we had this kind of situation, right? So we had the kind of situation people were beginning to run experiments in federated learning, in using some sort of IoT peripherals or network traffic fingerprinting, right? So federated learning, everybody knows what that is. Network traffic fingerprinting is the sort of thing where I open a refrigerator, it sends a message, and I can go the other way. I can look at the messages that were sent on the network, and I can see that, oh, Kate, did this just stop? Still works, okay. So it's kind of a bad look for an experimental test bed if people want to run experiments and the only way they can experiment is via some sort of simulation or emulation. So working with our users, we decided to figure out how to add those edge experimental resources to the test bed, start doing edge to cloud experimentation. Wrong button. So the first idea on how to do that came from our users is we wanted to work exactly like Chameleon works right now. So we wanted to be a cloud, but with edge resources. But then very quickly people started saying is, well, those resources are not usually in the data center, right? They are typically somewhere out in the field and they're connected to something like a camera or some environmental sensors. And there's a reason why they are there and in the data center, right? If the camera is not in your data center, shouldn't be there. And those resources are also not server class, right? So they edge resources, we define them as something that more or less runs Linux, right? Because that has a lot of mainstream support, but not very powerful and not very power hungry is the main thing. Because if you're going to deploy them in the field, you might not have access to a lot of power. So out of that came this sort of basic design where we do reconfiguration via container deployment, because this hardware doesn't support IPMI interface. So container deployment, very lightweight. We provide a framework for managing, for adding IoT peripherals. But then we also add users to add their own resources to the testbed, right, via something we call bring your own device. So what the users get out of that is a secure management for their resources, potentially deployed at large scale, that connects seamlessly to resources in the data center, right? So the rallying cry for that was, we want to support edge to cloud experiments from one Jupyter notebook, right, seamlessly. And so now, what can happen if you have infrastructure like that? How can you use it as an instrument? What can you measure? So some years ago, one of my colleagues at University of Chicago, my office neighbor, came up with an idea. He's a broadband researcher, Nick Feimster, very bright guy. And he came up with this idea that he wanted to measure access network, he wanted to measure broadband, but he had to do it in people's homes. There's no other way to measure it. So the idea was that he will reprogram some routers and hand out routers to people. They will deploy them. He'll get the data, they get the routers. Okay, great deal for everybody. It didn't quite work as planned, right? So if you put some extra stuff on the router, it interferes with the primary function of the router, and people don't like that. So he said, okay, next iteration, next idea is I'm going to take Raspberry Pi, plug it into the router, run tests from the Raspberry Pi, see what happens. They deployed about 30, and then they had to upgrade, and then it was like pedaling into the lake. It's all exhilarating till it suddenly stops, right? So how do we upgrade those Raspberry Pis in people's homes? So then he came to me and said, Kate, you've got this cheat edge stuff. You deploy a bunch of edge devices. Can you make this work? And I said, well, are you users computer scientists? No. How many of those Pis do you want to deploy? About 1,000. So that was a bit of a challenge. I said, let me write another proposal. And that proposal got funded, and this is the next project I said I would be talking about. So first of all, we bought 1,000 Pis. And why 1,000? Because 2,000 would be too many, and 900 would be too few. So 1,000 seemed like a good number. So then, how do we manage those devices, right? The original problem there. Well, it's good. This is, we're deploying in people's homes. There are security considerations. We did what we do normally, which is go back to the mainstream, try to ground things in the mainstream at the special sauce. And we found a system called Open Balena that gave us a lot of what we wanted, gave us the ability to manage hardware without physical access reliably. Primarily gave us secure management, secure upgrades to that hardware, all of those things. We did have to add some creature comforts there, like HA control plane, high availability control plane, federated identity access, a dashboard to manage those devices scalably, creature comforts, things like that. Are we there yet, right? Does this mean that the system is done? Well, it does not, because the problem is Nick has many friends, and they're all broadband researchers. And there are no two networking researchers who want to measure the same stuff or to want to measure it the same way. And if you talk to them a month from now, they will tell you a different thing again, right? So those things need to change, and you can't really vet people's images to the same standard that we can vet our images that we deploy that manage the system. So we need the cheat edge mechanism of deploying things that are isolated in a box, and we deploy containers on those devices. So we've got now this application management layer that deploys containers. Like in Chameleon, you can make advanced reservations on this. You can say, run this broadband test every hour on the hour and go from there. Now, once those broadband tests start executing, they generate data. The data is sent to the cloud. And then in the cloud, we had a bunch of services that were catching this data, processing this data, collating it, making sure that it gets into the right repositories. Okay, so we build a scientific instrument. We built an instrument that we can deploy nationwide, and we have to an extent. I'll talk about that shortly. How can we adapt this instrument? How can we tweak it, right? So if you have a telescope, you can adapt this telescope by pointing at a different area of the sky. You can ask different questions. You can adjust the optics, right? Well, in our case, we can deploy a different measurement application. And then finally, especially like from telescope array, you get data from the various different telescopes. You stitch them then into a picture of the sky. And in our case, is we can get data from those devices, and it gives us overview of what broadband is in a neighborhood or in a location. And then, of course, we can ask different questions of the data. So I'm going to go through how we do that with Float. So first of all, as far as deployment goes, well, so far we deployed 500 devices, right? So we got the devices about 18 months ago, 500 so far. And if you go to this URL, you will see interactive map of those deployments. There are some snippets here. But one thing I wanted to call out is that this is actually enormously hard. Deploying stuff in the field is enormously hard. So you've got some pictures here of us working with various communities at various events to hand out the devices to places where they can be deployed. Well, second thing, this is what I said earlier. Nick has many friends. So Metrics is the system that he develops, but different groups develop different systems. So those are the ones that run on Floto now. Those are the ones that different people have deployed. And so, for example, this radar toolkit measures quality of experience for just telehealth applications, right? So not interested in quality of the broadband really, just does it meet the needs of my application? And then lastly, the data set. So since project inception, since we started creating data, we created about 18 million different measurements that span different providers and that span different technologies. And it's publicly available, so we managed to do the IRB review for that. And we recently proposed it as an AIR data set because people are already doing research in, for example, anomaly detection. And sort of interesting graph of how the data set grew with the project deployment. Okay, so we deployed devices. Various people deploy their measurement applications on those devices, and we collected a large data set. But what good is all of this, right? So like with Chameleon, we had so many users and so many projects, but then the real clincher is that there were so many papers. There were papers, there's real research coming of this infrastructure. So here are a couple of examples of the kind of research that comes out of this infrastructure. And then again, I want to emphasize we just deployed the devices 18 months ago, not a lot yet. So here's a computer science example, which is IPv4 versus IPv6, right? It turns out that the speeds degrade differently in various conditions, right? Now, what are those conditions? This is what I'm saying that broadband scientists, if you ask them a few weeks from now, they will tell you they want to measure something else, right? Because they find a phenomenon, then they need to drill down, they need to change their tests, they need to measure a different thing. So this is one thing we're doing. Second example is policy questions. We actually had quite a few results in this space. So this is a result from Marion County, where we deployed a few dozen devices. And what they showed is that the broadband access in Marion County in about a third of the sampling was below FCC threshold. So they use this data to support grant applications for broadband expansion. We had a similar situation in Beaver Island, which is the worst internet in the country kind of thing. And that one was used to challenge broadband maps, FCC broadband maps, and they are doing it, we're doing wireless, we're doing broadband for the whole island. So what's next here? The next challenge, next frontier for broadband measurement for us is rural broadband. Now, rural broadband has the opposite problem to urban broadband. Urban broadband oversubscription is the problem. You go out into rural areas, it's the opposite problem in that you don't have enough subscribers, right? It's too sparse. So what we're going to do is put those, what we have done, in fact, as a pilot project for now, is put those devices on vehicles. The vehicles go around, devices record location, and measure. So then you have measurement correlated with location. Location is mobile. Yeah. In order to do that, we need to put GPS devices on the Raspberry Pis to measure the broadband. There's also another reason for GPS, which is time resolution. So here we're measuring one-way latency in urban areas. Ping-pong latency is fine. Here we're measuring one-way latency, which requires synchronizing time. And then a couple other projects that are just swing by. This is collaboration with NCAR on 3D printed weather stations. So they collect data about the environment, they put them in those 3D printed casings, and then they can reason about the environment based on that. We're augmenting that by adding Raspberry Pis as a low-LAN connection points that then have more robust connection to the cloud. Here's another one, instrumenting buoys with various environmental sensors. Here's a sort of more interesting one from the perspective of edge-to-cloud continuum. It's a project that a couple of our students did 2 years ago. And it started by our user in Rutgers who is teaching autonomous driving. So he's using self-driving cars really to teach machine learning to students. It's a fun kind of thing. And he works with Donkey Car, which is a package that was published by NVIDIA some years ago. And the package allows you to collect data by driving a car, or it has a simulator that you can use as well. Then you train models in the cloud. So the data gets streamed to the cloud, then you train models in the cloud. And then you verify them either via autonomous driving. So you can, buy a self-driving car connected to a Raspberry Pi from Amazon for $200. So you can verify them, or you can verify them by a simulator. So this is a lot of fun for the kids because they see AI in practice, in particular their models in practice, right? But it also allows them to spin out their own research projects. So for example, you can use the simulator, and then you can use the actual driving to create a digital twin experiment. So very much going from the edge to the cloud and back again, right? You can do that from one Jupyter notebook. You train the models in the cloud, potentially retrain them or refine them as they drive the car. And those were some examples. I don't have the time to cover everything, but we've got some fantastic other examples in federated learning, precision agriculture. Soundscaping is amazing. We also work with places like Iowa Flood Center that measure that measure flood likelihood over the state. Okay, so a few parting thoughts. I didn't get the 3 exclamation marks yet, but so a few parting thoughts. First of all, huge opportunities at the edge for AI, right? So increasingly computing is leaving the data center, going out to the edge where it can interact with the environment, where it can do intelligent data collection like we've seen with Floto, federated learning and other patterns. Then secondly, when people think about edge-to-cloud continuum, they typically think about processing capability that goes out of the data center into the edge. But there's more to it than that. In fact, it's a layer over layer over layer of different types of continuum. For example, when you think about data center, you think at the level of a power station. If you think about the edge, you typically dealing with some sort of solar power battery or a little windmill thing that powers your device, and that power is low, it's intermittent, it's unreliable. You have to adapt to those situations. Connectivity continuum, different networking conditions in the data center where you actually control the networking, different conditions at the edge where you not only don't don't control the networking, but you also have to worry about the host network being attacked, right? So you worry about more liabilities. And then there's, of course, the configuration continuum from, in our case, bare metal in the data center to container deployment at the edge. And lastly, there's operations continuum, right? We're living now in a world in which users are the operators, and making it simple enough, making those operations simple enough so that anybody can do that, so that anybody can deploy the devices, is a challenge in itself. So Chi at Edge captures a general purpose continuum research infrastructure, general purpose pattern. But some things we noticed are the same, right? So, for example, we have to manage all those devices at scale, right? This is the same from one application to another. Interactions with it from a data center is a very common pattern that the devices generate some data that you have to catch somewhere at the data center side and organize. But some things are different. For example, installation, encasing. It's different requirements when you deploy them in the wild, in weatherproof cases, different deployments when you're deploying it different deployment requirements when you're deploying in somebody's house. Okay, and last, I promise, I heard David Patterson being mentioned already today. He wrote this lovely editorial entitled "For Better or Worse, Benchmarks Shape a Field," in which he made the point that benchmarks are essentially a common denominator, right? A common denominator that allows us to compare between different approaches, and as such are essential to stimulating the debate in the field. Even more so, this is true about scientific instruments, like in particular test beds, right? So we have test beds give you the ability to deploy, observe, measure, and record. It's very hard to do an experiment, a viable experiment, and prove your results without doing that, right? So a common denominator in the sense that they give you the ability to create, but also the ability to compare because different people have access to the same resources. But in order to serve the debate, in order to stimulate debate, the test bed also need to evolve. And how we evolved from the data center into the edge is one example of that. And now I'm really done.
Thank you very much.